Hello, this is Math 2270 from the College of DuPage, coming to you during the summer of 2020, and this is the conclusion of a lecture entitled Higher Order Linear Differential Equations and Such Preliminaries. Any function y sub p, free of arbitrary parameters, that satisfies 7, and this is what I mean by equation 7 down here is a non-homogeneous equation, is said to be a particular solution. That's where the p comes from, or particular integral of the equation. Now this is where we're going then. Previously we found the complementary solution of the associated homogeneous differential equation, which was up here. That's called y sub c, and we're calling this operator c. This is L of y sub c is equal to 0, and this is L of y sub p gives me g of x. But then the general solution we're going to see in the following theorem is y, the general solution, is going to be the sum of the complementary solution and the particular solution. And that's what this theorem tells us. So if y sub p is any particular solution of the non-homogeneous differential equation 7, and I show you 7 again down here, and if y1, y2 through yn is a fundamental set of solutions of the associated homogeneous differential equation 6 on I, then the general solution is a linear combination of these linearly independent solutions and y sub p. Moreover, if the right-hand side of the non-homogeneous equation is the sum of different g sub k's, then all I have to do is add the solutions, the particular solutions for each of the g sub i's together, and I have a solution to this one. We have another superposition principle that holds for non-homogeneous equations. Now, I think this will hang together better if we work through an example. And some of this stuff is going to be new stuff, but I think this will help us see what's really going on. So I'm asking you to solve the following initial value problem. So here is L of y is equal to a g of x, or g of t actually. And we have initial conditions, this and this. You know what to do. Let's see how you did. I've listed the problem again up here just for our reference. So what we're going to do is we're going to be trying to find the solution, and it's going to be the sum of the solution, the general solution from the homogeneous equation, and where this would be 0, and a particular solution where I'll get this as a right-hand side. So let's begin with the homogeneous equation. So what we have is this is equal to 0. That is the homogeneous equation. And you can think about this as being d squared minus 4d minus 12 operating on y is equal to 0. Now, I have not proven, but will soon, but we have reason to believe from the example I did before that this has a lot to do with the polynomial, the quadratic r squared minus 4r minus 12 equal to 0. Now, if I factor this, which I can, I will find out that r1 is minus 2 and r2 is 6. So I have reason to believe that e to the minus 2t is going to be a solution and e to the 6t is going to be a solution, and moreover a linear combination of those should also be a solution. And finally, if I looked at the Wronskian of this and this, I would find that it is not equal to 0 anywhere. So you see, any solution to the homogeneous linear second order differential equation is going to be a linear combination of these two functions. Let's pause there and consider the non-homogeneous. Now we're looking at this and we would like to find a particular solution. Now notice that we have an e to the 5t over here. And anytime we take the derivative of a multiple of e to the 5t, there will be an e to the 5t popping out. So let's assume that we have a solution that is y sub p of t is a, an unknown constant yet to be determined, times e to the 5t. So we're going to take this assumed solution and substitute it into this left-hand side and set it equal to the right-hand side. So when we take the second derivative, we will get this. When we take the first derivative, we will get this times minus 4. Minus 12 times this is equal to that. And we will simplify. So we will have minus 7a e to the 5t is 3 e to the 5t. Now e to the 5t is not equal to 0, so I can divide all the way through and solve for a, and I find out that a would have to be minus 3 over 7. So you see, we have come up with a particular solution that works in this non-homogeneous equation, and it is y sub p of t is equal to minus 3 over 7 e to the 5t. Now, the big theorem that we talked about said the general solution of this then is going to be of the form a linear combination of the solutions, the fundamental set, linear combination of the fundamental set associated with the non-homogeneous plus the particular solution that we found. To find out what C1 and C2 are, I'm going to use the initial conditions, and first I have to take the derivative of that, which will give me this. You should verify all of these steps, and when I have these, I can substitute 0 in. E to the 0 is always going to be 1. I will get 2 equations and 2 unknowns. You know how to solve those, and when you solve those, you'll get C2 is 2 and C2 is 1 and C1 is 2. That means the unique solution to this non-homogeneous equation is y of t is equal to 2e to the minus 2t plus e to the 6t minus 3 over 7 e to the 5t. Just to review some different terminology that's sometimes used. A dynamic system whose rule or mathematical model is a linear nth order differential equation shown here is said to be an nth order linear system. The n time-dependent functions y of t, y prime of t, all the way up through the n minus first derivative are called state variables of the system. Recall that their values give the state of the system. The function g of t, the right-hand side, is variously called the input function, forcing function, or excitation function. A solution y of t of the differential equation is said to be the output or response of the system. Under the conditions in the theorem, the output or response is uniquely determined by the input and the state variables at a specific time t0. Those are the initial conditions. For a dynamical system to be a linear system, it is necessary that the superposition principle works. That means response of a system to a superposition of inputs is a superposition of the outputs. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and each other. God bless you all.